There's a clear shift for many in the data industry. We're the point where traditional data engineering principles align with new AI innovations to help ensure quality and automated memory management are converging. And that's what we're exploring in this week's deep dive based on the Data Pro newsletter from May 13, 2026. If this version's a little bit TLDR for what you're doing right now, you can head over to our YouTube page and check out a summary version of this video from the Data Pro newsletter that we mentioned. It's all there on the front page, it's easy enough to find, and while you're there, why not hit that subscribe button so you can get these updates sent to you directly.
Imagine trying to run a global logistics network on a dirt road.
Right, yeah. Not ideal.
No, exactly. You have this fleet of advanced high-speed delivery trucks, but the infrastructure beneath them is just full of potholes, unmarked intersections, fragile wooden bridges.
Sounds like a complete nightmare.
It is. But for the last 3 years, that is exactly what data engineers have been trying to do with artificial intelligence.
Oh, absolutely.
I mean, we've been building these massive enterprise-critical applications on top of, unpredictable, stateless chatbots. And fragile scripts.
Lots of duct tape.
So much duct tape. We just tape these incredibly capable language models to our systems, cross our fingers, and hope the internet connection doesn't drop mid-generation.
Right, because if it does, you lose everything.
Exactly. But today, the dirt road is officially being paved over. The era of prompt engineering as a competitive advantage. The idea that whoever types the most clever, perfectly worded instructions into a chat box wins, that's just over.
Yeah, the competitive moat has completely shifted. I mean, the real advantage now belongs to the teams who stop treating AI as this magical oracle.
Right.
And start treating it as a boring, reliable software workload. We're looking at a landscape that has totally abandoned the illusionist show for heavy-duty plumbing.
Which honestly is the best kind of plumbing.
It really is.
Yeah.
And the recent Anthropic Code with Claude 2026 keynote, they made a quiet but monumental statement by focusing almost entirely on that infrastructure.
And that is our mission for you today. We are breaking down the core thesis from a very insightful analysis on datapro.news called Agent Runtimes Are the New Layer in Data Stacks.
It's a great piece.
It really is. We are going to explore the mechanics of how agent runtimes are radically transforming daily data engineering workflows.
Which is huge for anyone in the field.
Definitely. We'll track this transition from simple prompts to reliable, production-grade systems, and we'll unpack the rigorous data quality checks that teams are now applying directly to the outcomes these agents produce.
Yeah, and for anyone listening who builds systems or manages data pipelines, I really want to emphasize this is not a cosmetic interface update.
No, not at all.
This is the exact moment large language models transition from being occasionally useful, slightly unpredictable assistants into schedulable, observable components.
Right, components within a highly governed production environment.
Exactly. The bottleneck is completely moved.
Because the frontier models themselves are finally good enough to handle long-running, complex work, right? Like tool-using work.
Right. The intelligence is no longer the limiting factor here.
So the friction point has moved to the machinery surrounding the intelligence. The orchestration loops, the harnesses, the evaluation systems.
Yeah, but before we get into the software architecture, we have to look at the physical reality making this possible.
Always comes back to the hardware.
It really does. You cannot spin up a global infrastructure layer without the raw physical compute to back it up.
So true. The physical substrate is the foundation of this entire shift. And the numbers coming out of the Anthropic platform are just staggering.
They are. We are looking at a 17-fold increase in API platform usage year over year.
17 times. That's insane.
It is insane. And to support that kind of hyper growth without the system just buckling under its own weight, you need an unprecedented expansion of physical data centers.
Right. Which brings us to the SpaceX Colossus One partnership.
Yes. We are talking about integrating more than 300 megawatts of new power capacity.
300 megawatts.
And bringing over 220,000 NVIDIA GPUs online within a single month.
Wow. Let's translate those massive numbers into the daily reality of an engineer. Because having 200,000 GPUs sounds great for Anthropic.
Sure does.
But what does that mean for the person trying to build a pipeline on a Tuesday afternoon?
Right, the actual end user.
Exactly. Well, it means limits are finally being lifted. The 5-hour rate limits for Claude Code have doubled across the board.
That's for Pro, Max, Team, and Enterprise tiers, right?
Yep, all of them. And they have entirely removed the peak hour limit reductions that used to, throttle systems when everyone logged on at the same time.
Oh, that was the worst.
It really was. Plus, the API rate limits for the heavy-duty Claw and Opus models have been raised significantly.
And those limit increases, they fundamentally change how you architect a system.
How so? Like, break that down for the daily workflow.
Okay, let's look at the historical pain point. A year ago, if you were a data engineer trying to run a heavy data extraction job over, say, 10,000 PDF documents using a frontier model.
You couldn't just write a script and walk away.
Exactly. You had to build complex back-off and retry logic. You had to constantly monitor for those HTTP 429 too many requests errors.
You're right. You were spending more time writing code to politely knock on the API's door than you were writing the actual business logic.
The API contention was a massive architectural constraint.
Yeah.
You were managing the traffic jam instead of driving the truck.
Which is so frustrating when you just want to get the work done.
And this is why dedicating a keynote to server capacity and rate limits, which sounds like the most mundane topic imaginable, is actually a massive signal to the enterprise market.
Because foundational technology isn't meant to be flashy.
Right. It is meant to be boring, predictable, and heavily instrumented. By leading with throughput and reliability, the message is that the platform can finally support heavy, continuous workloads.
Without forcing the engineer to babysit the API connection.
Exactly.
But hold on, let's look at the physical reality of 300 megawatts and 220,000 GPUs.
Okay, let's do it.
Those processors are not floating in an abstract cloud. They generate massive amounts of heat, they require immense power, and most importantly, they sit inside physical buildings.
Buildings governed by specific national laws.
Right. The compliance brick wall. This is a crucial reality check for anyone building in regulated industries like healthcare, finance, government.
Oh, absolutely. Compute at this staggering scale brings up immense considerations regarding data residency.
And in-region infrastructure requirements, supply chain security, all of that.
Yeah, you cannot just stream sensitive patient records or unreleased quarterly financials to a black box server rack sitting halfway across the world.
No, the legal team would have a heart attack.
They really would. There's a growing demand for localized infrastructure, which is why we are seeing expansions into dedicated Asian and European data centers.
Right. And the subtext here is that as you transition your agents into infrastructure, those agents inherit every single compliance headache of a traditional data platform.
Every single one. Your agent runtime is now subject to the exact same physical logistics, geographical constraints, and regulatory audits as your Snowflake data warehouse.
Or your AWS S3 buckets.
Exactly.
Okay, so moving from the physical data center to the software layer is where the daily workflow of the engineer actually changes, right?
That's where the rubber meets the road.
Right. We need to examine what this new vehicle looks like on our newly paved superhighway. Which brings us to the concept of cloud-managed agents.
Yes. This is positioned as a pre-built, highly configurable agent harness running directly on managed infrastructure.
And it is designed specifically for long-running tasks and asynchronous work, right?
Exactly. The whole goal is to eliminate the need for an engineering team to duct tape together their own agent loops.
Which saves so much time.
Oh, massive amounts of time. No more building your own state management databases or writing your own tool execution layers from scratch.
So the architecture is built on 4 distinct pillars, right? The agent definition, the environment, the session, and the event.
Notice that vocabulary?
Yeah, it's very specific.
Definition, environment, session, events. That is the nomenclature of a distributed systems job runner, not a chatbot.
Okay, let me push back on this claim a bit.
Go for it.
Because my team has been building Python scripts with while loops to call APIs for over 2 years now.
Sure, a lot of teams have.
Right. We give the model a prompt. We give it a scratch pad, and we loop the API calls until it spits out an answer. Under the hood, isn't this managed agent concept just Anthropic, providing a fancy user interface wrapper for a basic while loop and a larger context window?
I hear that a lot, but no.
Convince me this is actual infrastructure and not just a convenience feature.
Okay, it goes much deeper than a convenience wrapper.
Yeah.
The fatal flaw in the ad hoc Python while loop is where the state lives.
Right, the state.
When you run a script locally or in a basic cloud function, the memory of what the agent is doing, the context, the downloaded files, the intermediate tool outputs, it's all tied to your client's active connection.
Right, so if your laptop loses Wi-Fi.
Or if your cloud function hits a standard 15-minute timeout, the process just dies. the task is orphaned.
And you lose all the intermediate work.
Exactly, and you have to start the massive context window from scratch, paying for all those tokens all over again.
So the state is completely fragile.
Exactly. With Claude Managed Agents, we are talking about server-side persistence and a dedicated containerized environment.
Okay, so how does that work in practice?
When a client system triggers a task, it spins up an isolated environment, a configured container template. Inside that container, a session begins.
And the client can safely disconnect entirely.
Yes. The agent continues working, perhaps for hours, utilizing a persistent file system attached directly to that container.
Okay, wow. So the data engineer's workflow shifts from writing brittle synchronous API calls to managing asynchronous service contracts.
Exactly. You kick off a managed agent job the exact same way you kick off an Apache Airflow DAD.
You send the payload, you get a job ID back, and your system goes to do other things.
Furthermore, the event stream acts as the nervous system connecting the container to the outside world.
Okay, what does the event stream actually track?
It logs every message, every tool execution, every internal reasoning step, and every status update.
So a client can reconnect an hour later, query the event stream, and check the intermediate files on the persistent file system.
Yes. And you can even steer the execution by injecting new instructions mid-flight.
That's incredible. It is an execution environment paired with a robust control plane.
Exactly. Because it operates as a true job runner, it integrates seamlessly alongside your traditional data warehouses and streaming platforms.
Okay, so if we have a robust, stateful job runner that won't crash when the Wi-Fi blinks.
Which is a miracle in itself.
Truly. The immediate next step in any data engineering discipline is scaling it up, right? We want to run jobs concurrently to drastically reduce execution time.
Of course, everybody wants to go faster.
But there is a very explicit warning in the source material about multi-agent orchestration. It tells us to temper our expectations about what parallelism actually means in this specific paradigm.
Yeah, we have to be realistic. The concept is Anthropic's multi-agent sessions. It allows one primary agent to coordinate multiple sub-agents within a single bounded session.
And the mechanics are fascinating. All of the agents in the session share the exact same container and the exact same persistent file system.
Right.
However, every individual agent operates inside an isolated session thread.
This is key. They maintain independent conversation histories and event streams. They cannot see what the other agents are thinking in real time.
And there is a hard architectural boundary, right? You are limited to 25 concurrent threads.
Yes. And that limitation of 25 threads is a massive indicator of how this tool is meant to be used.
To visualize this structure, imagine you are a lead researcher standing in a massive library.
Okay, I like this analogy.
You have 25 highly specialized research assistants. You send them all out into different wings of the library simultaneously.
Right, they all scatter.
Each assistant has their own private notepad that represents their isolated session thread. They are furiously taking notes, completely unaware of what the others are discovering.
They're their own little bubbles.
Exactly. However, there is a central table in the middle of the library that is the shared persistent file system.
Okay, making sense.
As each assistant finishes a subtask, they walk to the table and drop their compiled notes onto it. Once everyone has returned, you, the lead researcher, read all the documents on the central table and synthesize the final overarching report.
The library analogy perfectly captures it. It's the structured scatter-gather pattern.
Right.
What data engineers must internalize is that this is absolutely not distributed computing in the traditional big data sense.
Right. If your background is in Apache Spark or Hadoop.
Where you take a massive data set of 1 billion rows, partition it into tiny chunks, and distribute bulk record-level transformations across a cluster of 1,000 commodity machines.
Yeah, this is not a replacement for that.
Definitely not.
Yeah.
You are not going to use a multi-agent session to calculate the daily active users from a petabyte of web logs.
Doing so would be incredibly inefficient and incredibly expensive.
Oh, astronomical cost.
Yeah.
The power of this controlled fan-out is in parallel investigation and multi-surface analysis for knowledge and code work.
Let's walk through a tangible scenario for that. Because theory is great, but what does this look like at 3 more a.m.?
The worst time for things to break.
Exactly. Let's say a critical service in your cloud infrastructure goes down at 3 a.m. Normally, an engineer has to sequentially open the AWS CloudWatch logs, then check the recent GitHub commits, then read the Jira tickets from the latest sprint to piece together what broke.
Which takes forever when you're half asleep.
Right. But with a multi-agent session, your coordinating agent spins up 3 parallel threads. Agent A is querying CloudWatch. Agent B is analyzing the GitHub diffs. Agent C is reading the Jira issue tracker.
All happening at the exact same time.
Yes. They all extract the relevant anomalies, dump their findings into a markdown file on the shared file system, and the coordinating agent instantly writes a unified root cause analysis.
You just collapsed an hour of frantic, sequential human investigation into 3 minutes of parallel agent work.
That is the daily workflow transformation right there.
Exactly. The data engineer's responsibility is no longer writing the parser for the log file. Their responsibility is architecting the orchestration of that multi-agent fan-out.
But this introduces a terrifying variable.
Oh, I know where you're going with this.
If I have 25 agents running concurrently, independently querying systems, extracting data, writing code, and dumping files onto a shared system, how do I establish any level of trust in what they produce?
That is the million-dollar question.
Because we all know the fundamental flaw of large language models is their propensity to hallucinate.
Yes, they are very confident liars sometimes.
They can produce an output that sounds incredibly confident, structurally perfect, and completely detached from reality. If I am parallelizing the generation of code, aren't I just parallelizing the creation of garbage? That's a great way to put it, a high-speed chaos engine. So the feature introduced to solve this is called outcomes.
Right. This is the mechanism that elevates an agent interaction from a simple conversation into verifiable work.
Let's break down the mechanics of an outcome because it bridges the gap between probabilistic text generation and deterministic engineering.
It really does. When you define a task in this new paradigm, you do not just provide an instruction. You explicitly define what done looks like.
You provide a rigorous, machine-readable rubric for quality.
Exactly. You set the acceptance criteria. The agent goes to work, generating the artifact. Maybe it's a Python script to migrate a database.
Okay, so the script is written, then what?
Once the primary agent finishes, the manage harness does something brilliant. It provisions a completely separate grader agent to evaluate the resulting artifact against your rubric.
A separate grader.
Yes. If the grader finds that the artifact fails the criteria, the system automatically loops back. It feeds the failure feedback to the primary agent, forcing it to iterate and try again until the outcome is met or a maximum iteration limit is reached.
And the most vital technical detail in that entire sequence is the separate context window, right?
Yes. The harness physically separates the generation environment from the grading environment.
Why is that separation so critical? I mean, if we are using the same frontier model for both tasks, why does it matter if the grader sits in the same session thread or a new one?
Oh, it matters completely. It solves the silent failure problem that plagued early AI adoption. We have to look at how the attention mechanism of a transformer model operates.
Okay, let's get into the weeds a bit.
The model assigns weights to previous tokens in its context window to predict the next word. If you ask a model to write a script, and it hallucinates an assumption.
Like, say, it decides to import a proprietary library that does not actually exist.
Perfect example. Those hallucinated tokens become part of its context. If you then ask that same model in that same chat window to verify if the script is functional, its attention mechanism heavily weights its own previous reasoning.
So it looks at the fake library it just invented, cross-references its own memory of inventing it, and concludes that it must be correct.
Exactly. It uses its own flawed logic to validate its own mistakes. It is grading its own homework while using the cheat sheet that contains all the wrong answers.
That is so dangerous.
Very. But by forcing the grader into a completely separate, sterile context window, you sever the AI's short-term memory of its own flawed reasoning.
So the grader agent boots up with a clean slate.
Yes. It only sees the rubric, the final artifact, and the grading instructions. It evaluates the code objectively without the cognitive baggage of the generation process.
It will immediately flag the non-existent library because there is no previous context tricking it into believing it exists. For the data engineers listening, this concept should be deeply familiar. I mean, we solved this exact architectural problem years ago with traditional data pipelines.
We did. If you build ELT pipelines, you know the absolute necessity of tools like DBT tests or grade expectations.
Right. You do not just move data from a raw table to a production table and assume it looks correct.
Never. You write a contract. You assert that a specific column cannot contain null values or that a user ID must be a unique integer.
And if the data fails the test, the pipeline halts.
We are taking the rigorous engineering principle of contract-based data pipelines and applying it directly to the probabilistic outputs of language models.
So, Just as a DBT test prevents corrupted data from destroying a dashboard, an outcome asserts that a generated Python script must pass a local linter.
Or contain no deprecated dependencies.
Right, and it must successfully connect to a test database before it is ever committed to the shared file system.
This fundamentally alters the psychological relationship an engineer has with the AI.
It really does. Think about the manual workflow of yesterday. You ask the model for a script. It fails.
You read the error, sigh, paste the stack trace back into the prompt box and type, "Try again, but fix this specific error."
It is an exhausting manual babysitting process. You are acting as the human compiler.
But by implementing outcomes, you transform that manual frustration into a structured, inspectable, automated iteration loop.
And the system gives you a per-criterion breakdown of exactly what failed, why it failed, and how many iterations it took to resolve.
It's the formalization of accountability.
I love that phrase, formalization of accountability.
It is the specific feature that transitions a managed agent from an ad hoc script you have to watch nervously into a trusted pipeline component you can comfortably schedule to run over the weekend.
You can actually sleep while the system works.
Imagine that. But
Wait, that introduces another incredibly complex layer, because while you were sleeping, your agents might be dreaming.
yes, the background memory compaction.
This is the feature categorized as a research preview, and it represents both a massive leap in efficiency and, honestly, a terrifying governance red flag.
It really is a double-edged sword.
Yeah.
Let's unpack the concept of dreaming, which is referenced in the documentation as dreams.
So we have established how outcomes ensure the output of an agent is high quality right now in the present moment.
Right.
But these managed agents are designed for long-running tasks. They are going to accumulate massive amounts of context, interactions, and memory over days, weeks, or months. What happens to all of that accumulated data?
Well, the standard industry approach up to this point has been naive accumulation.
Just hoard everything.
Pretty much. You take every single interaction, every log, every output, and you shove it into a massive vector database. And you rely on retrieval-augmented generation or RAG to find the relevant pieces later.
But the larger the vector database grows, the noisier it gets.
Oh, incredibly noisy.
Yeah.
You end up retrieving contradictory information, outdated instructions, and irrelevant context.
Which confuses the model. So dreaming introduces an active, asynchronous memory management process.
Exactly. Instead of just hoarding data, the system asynchronously reflects on its past sessions to reorganize its internal memory store.
It actively merges duplicate entries, right?
It does. It replaces stale information when a new fact contradicts an old one. It synthesizes discrete events into broader insights.
So it treats memory not as a static archive, but as an asset requiring continuous compaction and deduplication.
Which, on paper, optimizing the memory store sounds incredibly efficient. It mimics how human consolidation works during actual REM sleep.
Right, but let me put on my system architect hat for a second.
Uh-oh.
Because this sounds like an absolute governance nightmare.
It can be.
If an autonomous system is running in the background, summarizing and rewriting its own foundational memory, what happens when it makes a mistake?
You are identifying the core vulnerability here.
Let's say an agent spent 3 weeks learning the intricate, highly specific compliance requirements of a new European client. And during a dream cycle, to save space, the model compresses all of those complex legal guardrails into a single synthesized memory that says, Client X prefers strict data privacy.
Wow, yeah, it completely erased the legal nuance.
Exactly. Or worse, what if it synthesizes 2 conflicting interactions and accidentally introduces a brand new bias that wasn't present in the source data?
That's a huge risk.
If this compaction happens automatically while I'm asleep, how do I even know what the agent altered?
And this is why the source material waves a massive red flag around this feature. The fundamental rule of data engineering is that derived data is still derived data.
It is an interpretation, not the raw source of truth.
Exactly. When you allow an AI to treat its own memory as data, you are walking into a minefield of untrackable state changes.
Because if data transforms without a paper trail, you cannot trust the system.
Period. If an enterprise team intends to use a feature like dreaming in a production environment, they cannot simply flip a toggle switch and walk away.
They must immediately enforce strict data management practices upon the agent's internal cognitive layer.
The daily workflow now requires the data engineer to audit the AI's subconscious.
Audit the AI's subconscious? That is wild to think about.
It is. It requires robust lineage tracking. You need an immutable log proving exactly which original session interactions produced which synthesized memory block.
You need clear definitions separating the raw authoritative event log from the optimized memory index.
Yes, and you must implement version control for the memory store itself. You need diffing tools.
Diffing tools, like to see the changes.
Exactly. The ability to visually inspect what changed between the agent's memory state on Tuesday versus its memory state on Wednesday.
Because if the AI corrupts its own operational context through a bad dream cycle, you absolutely must have a rollback capability.
You need a button to restore the agent's mind to a known healthy state.
So the concept of dreaming is profound because it forces traditional data governance practices, lineage, auditing, versioning, rollback directly into the internal architecture of the model itself.
That's exactly it.
Okay, we have mapped out an incredibly sophisticated system here. We have robust managed containers on top of 200,000 GPUs.
We have parallel orchestration using 25 concurrent session threads.
We have rigorous quality gates through outcomes with separate context windows.
And we have asynchronous memory compaction governed by version control.
This is a marvel of software engineering. It really is.
Truly.
But let's step out of the architecture diagram for a minute and look at the accounting ledger.
The bill.
Because running an army of frontier models with all of this overhead at enterprise scale is going to result in a computing bill that will completely bankrupt a company if left unchecked.
The economics of inference. That is the practical brick wall every single AI initiative eventually hits.
Because tokens are not abstract units, they represent expensive GPU cycles.
Right. Pushing 10 million tokens a day through a frontier model is financially unsustainable for most daily workloads.
Which brings us to the operational necessity of the advisor strategy.
Yes. The keynote highlighted a shift toward cost routing architectures as the default standard.
So what is the advisor strategy exactly?
It's a tiering mechanism. You route the vast majority of your heavy repetitive workloads to a much smaller, cheaper, and faster model.
Okay.
You only consult the highly capable, highly expensive frontier model like Claude Opus when a task is exceptionally complex or when the smaller model fails.
So you don't just use the biggest hammer for every nail.
Exactly. And the impact of this architecture is immense. The keynote cited an enterprise customer who maintained frontier model quality across their pipeline while reducing their overall inference cost by a factor of 5.
A factor of 5. Achieving a 5x cost reduction while maintaining quality is the holy grail of system design.
It really is.
It perfectly mirrors the concept of tiered storage in traditional data engineering.
Oh, absolutely.
I mean, we keep our hot, frequently accessed, mission-critical databases on expensive, blazing fast, solid-state drives.
And we migrate our cold, archived, or less critical data onto cheap, slow-spinning disks or tape drives.
We don't put everything on the expensive hardware because it's a waste of money.
Right. Here, we are not tiering storage. We are architecting tiered intelligence.
Tiered intelligence. That is the exact paradigm.
And for data engineers, managing tiered resources is muscle memory. You are accustomed to reserving your most expensive compute clusters for the specific edge cases that demand massive parallel processing.
Right, while running standard ETL jobs on smaller, cheaper nodes.
Exactly.
But how does this tiering actually manifest in a daily, high-volume workflow? An engineer cannot sit at a dashboard all day, manually reviewing thousands of tasks and deciding, oh, I'll send this batch to the cheap model and I'll send this specific complex query to Opus.
No, it has to be programmatic. The tiering cannot involve human routing.
So how does it route automatically?
The workflow requires setting up automated escalation matrices. And this circles back beautifully to the outcomes feature we analyzed earlier.
Oh, the quality gates become the routing mechanism.
Yes. The rubric dictates the escalation.
Let's trace the life cycle of a task through this matrix.
Okay, walk me through it.
So a complex data extraction request enters the pipeline. The system defaults to routing it to the fast, inexpensive model.
Right.
The small model generates the extraction script. Then the separate grader agent evaluates that script against the strict outcome rubric.
Yes.
If the script passes, the job is complete, and you spent pennies on inference.
Which is the ideal scenario.
But if the artifact fails the rubric and fails the maximum number of automated retry loops,
That failure event triggers the escalation.
the pipeline automatically packages the failed artifact, the rubric, and the error logs, and hands the entire bundle up to the expensive Opus model to resolve the final mile.
You only pay the premium toll when the system algorithmically proves it cannot solve the problem cheaply.
That is so elegant.
It is.
Yeah.
And you can also build escalation triggers based on other heuristics.
Like what?
Well, if the small model returns an uncertainty score below a certain threshold, escalate.
Makes sense.
Or if the task involves a high-value business system like LEN, modifying a production database schema, you might bypass the small model entirely and route directly to the premium tier.
So inference routing is no longer just a clever hack to shave a few dollars off the monthly AWS bill.
Definitely not. It is the fundamental economic architecture required to run model-driven infrastructure at a global scale.
We have covered a tremendous amount of conceptual ground today, mapping the entire journey from physical data centers to economic routing.
It's a lot to take in.
It is. So let's synthesize this entire transformation for you, the listener. What this deeply technical analysis reveals is that artificial intelligence integration is no longer an application layer novelty.
It's past that phase.
It is no longer the domain of hobbyists trying to trick a chatbot with a clever prompt.
Right. With the deployment of managed execution containers, controlled parallel fan-outs, rigorous quality gates like outcomes, the complexities of governing internal memory, and the economic necessity of tiered intelligence routing.
Agent harnesses are definitively, undeniably production infrastructure.
The paradigm shift is complete. The tools have matured into standard data components.
So if you are an engineer who currently builds Airflow-directed acyclic graphs, if you write DBT tests to validate data transformations, if you instrument observability dashboards to monitor pipeline health,
You already possess the exact architectural mindset required for this new era.
you do not need to learn how to be an AI whisperer.
No. You simply need to apply your rigorous engineering discipline to a new type of non-deterministic compute.
However, there is an unstated, almost unnerving trajectory implied by everything we have just discussed.
Yeah, there is.
Something not explicitly detailed in the source material, but a logical endpoint you must consider.
The infrastructure loop.
Right, the infrastructure loop. We have spent an hour detailing how managed agents can now write complex code, utilize external tools, and have their work rigorously evaluated by separate grader agents against strict algorithmic rubrics.
They are evaluating and correcting each other based on rules defined by humans.
The agents are managing the code.
But if the agent runtime itself is now simply software infrastructure, just standard containers, persistent file systems, and configuration APIs.
Right.
And if these agents are now demonstrably reliable enough to manage code and provision infrastructure.
It raises an inevitable architectural question.
It does. How long will it be until we see agents utilizing these exact outcome evaluation loops to rewrite, optimize, and provision their own runtime containers?
An agent identifying a bottleneck in its own performance, writing the infrastructure as code to expand its own container memory, grading that configuration file for safety using a separate context window, and deploying the upgrade.
A self-optimizing system expanding its own operational substrate without a single human data engineer required in the loop.
We began this deep dive discussing how the illusionist's magic show has been replaced by practical, heavy-duty plumbing.
Yeah.
But if the plumbing reaches a level of sophistication where it begins autonomously designing and laying its own pipes,
That is a completely different, infinitely more powerful kind of magic.
it forces us to redefine what the role of the human system architect will be in the very near future.
It certainly does.
Well, we want to thank you for joining us on this incredibly detailed journey through the new data stack.
It's been great.
As your daily workflows shift from writing prompts to orchestrating pipelines, keep looking closely at the mechanisms under the hood.
Keep demanding to know how the state is managed, how the quality is guaranteed, and how the infrastructure scales.
Because the dirt road is being paved over faster than any of us imagined, keep questioning the systems you build. Until next time.
Thanks for checking this out today. Don't forget you can connect with other data professionals worldwide on our growing school platform. It's all linked in the description, so pop along, come in, have a chat, and check out the exclusive resources there for data professionals like you. And if you haven't done so already, please feel free to like, share, or subscribe to the channel.